Ωραία. So, καλησπέρα σε όλους. Welcome everybody. We are very pleased to have today with us Maria Charisi, Dr. Maria Charisi. I met Maria several years ago in the United States, and I haven't seen her for quite a long time now, so I'm really glad that I will be able to listen to her research and the progress that she has made in the last couple of years. A few words about Maria. Maria graduated, took her bachelor diploma in physics from the Aristotle University of Thessaloniki in Greece, but then she moved to the United States in order to pursue a degree, a PhD degree. She graduated from the University of Columbia in New York, where she worked under the supervision of Professor Zoltan Hyman. Since then, she has received several fellowships. One of them was the NANOGrav fellowship, where during this period, from 2017, if I remember correctly, till 2020, she worked in the Tapir Institute at the Caltech University in the US. And after that, she also received another fellowship from the Vanderbilt University, the Vanderbilt Initiative for Data Intensive Astrophysics Fellowship. And she's working there as a postdoctoral fellow. And as I have learned today, she has received a tenure track position at the Washington State University, where she will be moving in January 2024. So this is big news, and congratulations to Maria. And a few words about her research. Maria is an expert she has been studying a lot supermassive black hole binaries, and she is very interested in time domain and gravitational wave astronomy, especially now in the multi-messenger era. So I'm very happy that we're going to listen to her today, talking to us about the search of supermassive black hole binaries in the era of multi-messenger astronomy. And Maria, the floor is yours. Thank you very much for accepting the invitation.
Thank you, Maria. Thank you for the invitation and for the very nice introduction. I'm very happy to be with you today. So I'm going to talk about the search of supermassive black hole binaries using both electromagnetic and gravitational wave observations, as Maria said already. And as you probably know, in the last few years, since the first detection of gravitational waves from two merging black holes, astronomy is undergoing a revolution. And in my mind, that revolution can only be compared to the first moment that Galileo pointed his telescope to the planets and started systematically observing and studying the night sky. Of course, in the beginning, we could only observe in a limited part of the electromagnetic spectrum. We could only observe in the optical band. But in the intervening centuries, as we developed the technology, we managed to observe across the electromagnetic spectrum, from the lowest energy photons in radio waves to the most energetic photons in gamma rays. And we have uncovered a much more rich picture of the universe from the first moments of the universe with the cosmic microwave background to the most energetic phenomena in our local neighborhood, the collapses of stars and so on. So gravitational waves will similarly revolutionize our understanding of the universe. But before I get to the details, let's first discuss what gravitational waves are. So gravitational waves are a prediction of general relativity, which is the theory of gravity. And in general relativity, every object that has a mass can curve the space-time. And every object that is moving through a curved space-time, it's the curvature of space-time that dictates its motion. And this is the equation of motion in general relativity. And it's the only equation I have in the talk, so don't freak out. So pretty much what this equation describes is what I already told you. Matter tells space-time how to curve, and then space-time tells matter how to move. One of the predictions of general relativity is gravitational waves. So gravitational waves are perturbations in space-time itself. every mass that is accelerating is producing gravitational waves. And these gravitational waves squeeze and stretch the space-time, like in the animation here. And they're transverse waves. So if the gravitational wave is coming towards me, it will make me taller and thinner, and then shorter and fatter, taller and thinner, and shorter and fatter, and so on. These waves propagate with the speed of light. And of course, I'm moving my hands around here, so I'm producing gravitational waves, but don't expect to see me deforming from these gravitational waves, because these are tiny ripples in space-time. And the reason they are tiny is because their gravity is weak. And we all have the experience of gravity being weak just by the fact that we can stand up, like the strength in our muscles can withstand the gravity of the entire Earth. So if we want to have any hope for detecting gravitational waves, we need extreme systems. So we need compact objects that are moving very, very fast. And that typically happens when we have a binary that is at the final stages of its orbit. And of course, as gravitational waves take away energy from the system, the orbit is accelerated. So the two black holes, let's say, move faster and faster. The frequency increases, and there is a maximum frequency where pretty much the two black holes will have merged. And that maximum frequency depends on the total mass of the system, and it's inversely proportional to the total mass. So if we have low mass systems, we have high frequency gravitational waves. If we have high mass systems, we have low frequency gravitational waves. And indeed, in the universe, we know that we have a great variety of black holes that span several orders of magnitude in mass. So we do expect that we will have a great variety of gravitational waves that also span a huge variety in gravitational wave frequency. The exciting thing is that unlike the electromagnetic spectrum, that it took us several centuries to open up the different windows, gravitational wave astronomy is an accelerated science, and we expect a lot of excitement within the next few decades. So let's dive a bit deeper to the gravitational wave spectrum. So here I'm showing the gravitational wave strain, which pretty much quantifies the squeezing and stretching of space-time as a function of frequency. And we have already opened the high frequency gravitational wave window with the detections from LIGO and other ground-based detectors. So LIGO, that can observe in frequencies of a few hertz to a few kilohertz, can detect binaries of stellar origins. Binary black holes, black hole, neutron stars, neutron star, neutron stars, and so on. And LIGO has given us a lot of excitement in the last 5 or 6 years. If we want to detect more massive systems, we have to go lower in frequency. So the next window is the millihertz frequency window, which will be accessible to LISA. LISA is a gigantic interferometer like LIGO that will fly in space, and the arms of the interferometer will be millions of kilometers. And LISA will be sensitive to the most massive of the stellar mass binaries, the least massive of the supermassive black hole binaries, and also to a class that is called extreme mass ratio in spirals, so small black holes of stellar origin falling onto supermassive black holes. The last window is in the nanohertz frequencies, and it's pulsar timing arrays, which is a galactic scale detector that aims to detect supermassive black hole binaries. And this will be, I will be talking a lot about this window today, because this is the next in line for discovery. So in this talk, I will first start by describing the source population of pulsar timing arrays, which are supermassive black hole binaries. And then pretty much the rest of the talk will follow my career path in this field. I will describe how we can use electromagnetic data to search for supermassive black hole binaries, then how we can use gravitational wave observations, and in particular Pulsar timing arrays to look for supermassive black hole binaries, and finally how we can combine the two windows, and what constraints we have so far, and what are the prospects for future detection. Now let's start from supermassive black hole binaries. What are these systems and why you should care about these? From observations of nearby galaxies, like our closest neighbor here, the Andromeda galaxy, we know that every massive galaxy has a supermassive black hole in the center with a mass from 1 million to 10 billion times the mass of the sun. And that central black hole is very important for the galaxy. We also know that through the history of the universe, galaxies often merge to build more massive, bigger galaxies. And that process naturally leads to a galaxy that will have two supermassive black holes, which eventually lose energy and angular momentum and progressively move to smaller and smaller separations. When they get to roughly a parsec scale, and for the physicists in the audience, a parsec is a few light years, and I will use this distance measurement unit a lot. So when they get to the parsec scale, they become gravitationally bound. And this is the stage that I will refer to as a binary. Now, another important thing to remember is that galaxy mergers typically involve a lot of gas. And that gas in a galaxy merger ends up in the central region of the post-merger galaxy. It can accrete onto the black holes and provide bright electromagnetic emission, which is very important for us because it can give us the signatures that will allow us to find these systems. Now, of course, if you noticed up here, there is a clock in the simulation, and the process of the galaxy merger can take several gigayears. So it's a very slow process, and for our human time scales, it's practically impossible to see the evolution of these systems. But we have tons of galaxies out there that we can observe, and we can catch them at different stages of their evolution, so we can piece together how these systems evolve. And we know now the rough stages that the black holes go through after the galaxy merger. So initially, they fall towards the common gravitational center through a process that is called dynamical friction. This is large-scale interactions with the gas and the stars in the post-merger galaxy. That process is efficient at bringing the binary down to a few parsec. Then roughly at the parsec scale, the interactions with the immediate environment become more important. So if there are stars around the binary that cross, let's say, the binary orbit, we have three-body interactions. The binary can act as a slingshot and expel the star to large distances. So through this three-body interaction, the star is gaining some energy. That means that the binary is losing some energy. But of course, the star is very small compared to the supermassive black hole binary. So we need many, many such interactions to have a significant effect and significantly reduce the separation of the binary. Another potential mechanism is related to the gas that I already told you we expect to be around the binary. The gas can also act as a catalyst to the binary evolution and remove energy and angular momentum from the system and push it to smaller separations. Now, when the two black holes get to small separations, small enough separations, gravitational waves can take over their evolution and bring the two black holes to the final coalescence. Now, of these three stages, the intermediate one is the one that is the most uncertain. We don't know if there is enough stars to bring the binary to small separations. We really don't know if the gas is pushing the binary inwards or outwards. And of course, the reason we have so much uncertainty is that we have never observed a binary at a separation less than a parsec. And of course, this is where my research has focused, and you will hear a lot about this today. Now, finding binaries at these final stages of their evolution is very important, both for extragalactic astrophysics and for fundamental physics. So I already described all the uncertainty we have in the process, the formation and the evolution of these binaries. There's a lot of uncertainty of how the binary interacts with the gas around it and produces the electromagnetic signatures. And of course, this is the last piece of galaxy mergers, which are an important component for galaxy formation and evolution. So finding this stage of black hole mergers, it is important for us to understand how galaxies form and evolve, how their black holes form and evolve and co-evolve with the host galaxy. And of course, we are talking about the most massive binaries in the universe. So they allow us to test relativity at its extremes. And of course, if we can find them at high redshifts, we can use them to do cosmology. So now that I hopefully have convinced you that supermassive black hole binaries are very important, I will just describe how we go about finding them. First of all, using electromagnetic observations. And very often, we observe the initial stages of galaxy mergers and the pairing of their black holes. So in the last 2 decades, we have observed a few dozens of galaxies that have 2 active supermassive black holes that are separated by kiloparsec distances. These are called dual AGN, and they have been resolved across the electromagnetic spectrum. Now, if we go to smaller separations at the parsec scale, we can only resolve the binaries in radio waves with very long baseline interferometry. And this example here is the record holding binary that has a projected separation of 7 parsec. Now, if we go to even smaller separations, not even telescopes like the Event Horizon Telescope have the required resolution to take an image and resolve the 2 black holes. So we need to find the method to infer the presence of the black hole from the effect it has on its environment. And one of the most promising methods to find binaries at their final stages of their evolutions is to find quasars with periodic variability. So now, why quasars? Quasars are galaxies that have actively accreting black holes, and they're very bright. And we think that at least a fraction of the quasars are activated by galaxy mergers through the merger perturbs the gas distribution in the galaxy and brings it to the center, so it activates the quasar. And for that reason, they're prime places to look for galaxies with 2 supermassive black holes. Now, why periodic variability? I would argue that this is fairly intuitive. As the binary periodically perturbs its environment, it should produce some periodic flux changes. But this is a prediction that has been confirmed over and over in multiple hydrodynamical simulations. So when we have a binary that we put it in a gaseous disk, what it happens is initially the binary acts as a propeller, and it pushes the gas from the central region outwards. So it creates this cavity of low density material, but that cavity is not completely devoid of gas. So as the binary interacts with the edge of the cavity, it pulls streams of material inwards that can fall onto the black hole and produce bright electromagnetic emission. So from these simulations, we know that binaries can produce bright quasar-like luminosities. And also, we expect that the luminosity will be periodic. For example, if we look at the accretion rate, so the feeding rate onto the black holes, we see that as a function of time, we see that it varies periodically. So if we take the periodogram of the accretion rate, we see a strong peak at the orbital period of the binary. So we expect that these binaries will produce bright luminosity that changes periodically over time. From the simulations, we also see that the evolution at this stage is relatively slow. So that means that binaries spend a lot of time at these small separations. and therefore they should be common, and we should be detecting them quite frequently. In fact, that animation won't play. So in the last few years, we had, hopefully that will play now, we had a lot of excitement from time domain surveys, which are surveys that systematically cover the sky and observe over and over and record the flux, the brightness changes of millions of sources over the course of years. And this animation shows how PTF, which is one of these first time domain surveys, covered the sky. And you can see that over the course of this survey that lasted for 4 years, we have fields that were covered with over 1,000 observations. So in the last few years, we had the data to look for this type of signal for quasars with periodic variability. And in fact, by analyzing pretty much all the available data that are out there, we now have about 250 promising candidate systems. Here I'm just showing a few examples of the main searches, included my thesis work with the Palomar Transient Factory. And of course, you may have noticed that here I emphasize the word candidate, because finding periodicity in quasars is extremely challenging. A few of the reasons are already obvious in these plots. The data are sparse and have long gaps. The periods that we are looking for are relatively long, so we cannot see many cycles of periodicity. And another reason, which is not as obvious, is that quasars have stochastic variability, which can mimic the periodicity. And for that reason, even though statistically we have taken into account the stochastic noise, we expect that there's a lot of contamination in these samples of periodic quasars. Now, confirming even one system would be a big deal. And there are 2 ways we can go about it. One is observe long enough and see whether these systems will remain periodic. Since we have periods of a few years, we may need to wait for decades to accumulate enough cycles. The other approach is to look, to take multi-wavelength data and look for additional signatures that could signify the presence of a binary system in the quasar. And in fact, I have done a lot of work here that I won't have time to get into it. But I will say the most exciting thing is that some of the candidates that we are still observing have multiple lines of evidence for a binary system in that quasar. The problem is that none of the signatures is unique, but since I won't have time to get into more detail than this, I will just refer you to this review that we wrote with Dan Dorazio, where we summarize all the potential observables for supermassive black hole binaries and all the observational work that has been done in the last few years. Now, this is a very exciting time because we will have the Rubin Observatory that will start operations in next year, actually. And the LSST, or the Rubin Observatory, will be a complete game changer for searching for quasar periodicities and for searching for supermassive black hole binaries. First of all, because the data that we expect from LSST will be of fantastic quality. And second, because it will observe a huge sample of AGN, 2 or 3 orders of magnitude bigger than the ones we have available now. And in that small sample, we expect even the more rare binaries to be present, the ones that will have periods of a few months. And if we manage to detect a short period binary, then over the course of the survey, which will last for 10 years, we will have 20 or even 50 cycles within the data, and then we can be certain that this system is a binary. Now, of course, I already described how challenging it is to find quasars with periodic variability, so maybe you are worried that in LSST we will be flooded with false detections. So I have some great news on that front. with a graduate student, Caitlin Witt, who is now a postdoc at Northwestern, we developed a Bayesian pipeline to select periodic signals on top of realistic quasar noise. And then we tested our pipeline with simulated data. And our simulated data represent current, let's say, quality of data, something like the Catalina survey, which is shown here, and what we expect for LSST, so the future capabilities. And we look at the true positive rate of our detection method versus the false positive rate. So real signals that we should be detecting versus noise that we falsely identify as signals. And the stars here are the detection threshold for our method. And you can see that in both cases, we find about 60% of the real signals. The stochastic noise of quasars doesn't allow us to find all the signals. But the big difference between current surveys and LSST is that we go from something that has a contamination rate of 20% to something that is close to 0. So the quality of the LSST data will be such that will allow us to identify very reliable candidates. And that concludes the electromagnetic part of the talk. So I will take a break here to see if any of you have any questions.
I don't see any questions, Maria.
Okay. We can leave them for the end. So I'll go on to the second way that the second method we can use to detect supermassive black hole binaries that relies on their gravitational wave emission, and in particular using pulsar timing arrays. So pulsar timing arrays rely on millisecond pulsars, which are the most precise clocks in the universe. And millisecond pulsars are magnetized neutron stars that they have collimated emission along the magnetic axis. And also they rotate very stably. So if the rotation axis is misaligned with the radiation axis, we get this lighthouse effect. So every time the radiation beam swipes our line of sight, we get a pulse that we can record with radio telescopes on Earth. And because they are very stable rotators, we get this repeating profile, which, because it's very stable, it's very precisely repeating. This signal, of course, is highly exaggerated. Pulsars give out very weak signals, and that's the reason why we need access to the biggest telescopes on Earth. And this requires a lot of the effort of many people and international collaboration. So here in the US, we have the NANOGrav collaboration, which stands for the North American Nanohertz Observatory for Gravitational Waves, of which I'm a member. In Europe, there's the European Pulsar Timing Array. In Australia, the Parkes Pulsar Timing Array. And recently, we have the formation of some newer pulsar timing arrays in India, China, and South Africa. Now we collect this data from all the radio pulsars we observe, and how do we use that to find gravitational waves? So we have gravitational waves produced in another galaxy that pass through our own galaxy, and they squeeze and stretch the space-time. So they squeeze and stretch the distance between the pulsars we observe and the Earth. So some of the pulses will have to travel a longer distance and some will have to travel a shorter distance. So instead of observing this precisely repeating profile, some of them will arrive sooner and some will arrive later. And if we see this along many pulsars, we can detect gravitational waves. So we need to see the signal in many pulsars to be certain that it's not one pulsar that is doing something weird. But we also want this signal to be correlated among the pulsars. What we call the Helms and Downs curve, which is what I'm showing here. So what I'm showing is the degree of correlation as a function of the angular separation between two pulsars. So we take a pulsar pair and we see the degree of correlation. Now, the derivation of this curve, it is mathematically complex, but I'll try to build some intuition here why we expect this curve. So, for example, let's say we have two pulsars from the same part of the sky. They will experience the squeezing and stretching of space-time at the same time. So we expect that their signals to be positively correlated. Now, if we have two pulsars at 90 degrees, when one is experiencing a squeezing, the other one is experiencing a stretching, and vice versa. So at 90 degrees, they should be negatively correlated. Then if we go to 180 degrees, again, they both experience squeezing and stretching at the same time. So the correlation should return to positive. So we have this quadrupolar pattern that we expect to detect. Now, pulsar timing arrays will detect two main signals. The first one is the stochastic gravitational background from the superposition of many unresolved binaries. And here I'm showing the characteristic strain again as a function of frequency. The background will have roughly a power law dependence on the frequency. And this background may be detected soon. The reason I'm saying that is because in the last data set that we analyzed as the NANOGrav collaboration, we found a power law signal in many of the pulsars, common in many of the pulsars in the array, that is consistent with gravitational waves. But we didn't find the characteristic spatial correlations that I was describing with the Helms and Down curve. So since NANOGrav found this signal, all the other major PTAs confirmed this detection. And this is very exciting because this could be the first hint of the gravitational wave background. And if we observe longer, then we may build our confidence in this signal. So with simulations, we can predict how the signal-to-noise ratio of the signal will evolve over time. And there are predictions that even in the 15-year data set, which is the last one that NANOGrav has produced and is currently analyzing, we may be able to separate the different possibilities. So that means that even in the 15-year data set, we may be able to make the first detection of the gravitational wave background. So we have already collected this data and we are currently are analyzing the data set. So stay tuned because this may be very exciting. And finding the background is very exciting, first of all, because we will open up, as I said in the beginning, a new window into the gravitational wave spectrum, but also because this background contains a lot of astrophysical information. First of all, the amplitude of the background, pretty much at what level we expect this power law to happen, depends on how often galaxies merge, how efficiently the binaries get to the gravitational wave regime, and also on the supermassive black hole mass function, pretty much how massive are the black holes in these galaxies that they merge. The amplitude of the background will be the first thing that we detect, but over the years, we will be able to constrain the entire gravitational wave spectrum. And that contains additional information about how these systems evolve. So for example, if the systems are in circular orbits and they only evolve due to the emission of gravitational waves, we expect the power law that I already discussed. But if we have other processes that drive the binary evolution, like the three-body interactions with the stars or the interactions with the circumbinary disk, they can also accelerate the evolution of binaries. So we expect that the binaries at low frequencies will spend less time at these separations as they would have spent if they only emitted gravitational waves. So the spectrum will be slightly different depending on what process is important. And also, if the binaries are not circular and they have some eccentricity, we also expect that the spectrum will be significantly different. So by constraining the spectrum, pretty much measuring what is the level of the background at different frequencies, We can learn about how these systems evolve and learn a lot about the population, whether the orbits are eccentric or circular, and so on. Now, except on top of the gravitational wave background, we expect to find individually resolved binaries that have loud enough signals to stand above the background, like loud voices in a crowded restaurant, let's say. And we expect that these systems will be detected 3 to 5 years after we detect the background. We typically catch these systems a long time before the merger. So thousands of years before the merger. So unlike LIGO that we see like a fraction of the second and the system merges, for our human timescales, these systems are practically eternal. So that is good news if we want to follow the map and find electromagnetic counterparts. And as I already discussed, we do expect that they will have bright electromagnetic counterparts. So that makes them very promising sources for multi-messenger observations. In fact, the supermassive black hole binaries may be the only type of sources we can do multi-messenger observations in systems that involve black holes. LIGO has already detected close to 100 binary black holes of stellar origin. None of them has a confirmed electromagnetic counterpart. But here, it's natural to expect that we will have bright electromagnetic emission on top of the gravitational waves. Now, why do we care about multi-messenger observations? Of course, the different messengers carry different information about the system. So gravitational waves probe the dynamics of the orbit and the gravitational field around the binary. And the electromagnetic observations probe the plasma conditions around the binary and how the binary interacts with the gaseous environment. So putting them together allows us to build the most complete picture of binaries. So before I move to the last part, again, I'll take a short break to see if you have any questions for that part. Okay, so since I'm not hearing anything, so I'll just move on to the last part of the talk, which is how we combine these gravitational wave observations and electromagnetic data to do multi-messenger science. Of course, as you know, we have not detected gravitational waves yet. And when we don't detect something, we typically place upper limits on that quantity. And here I'm showing the sky map of upper limits for individually resolved binaries. The pulsars that we observe are the stars in this map. And you can see that at the part of the sky where we have more pulsars, we have greater sensitivity, and the limits we can place are more stringent and more informative. Of course, if I show you this map and point to some part of the map and say the limit is 10 to the minus 15, I'm sure that doesn't tell you anything. But if I tell you that in, for example, M87, we can exclude the presence of a binary for that range of frequencies and that range of masses, it's more informative astrophysically. So one of the projects that I led for the NANOGrav collaboration was pretty much to put these limits into astrophysical context. So I built a galaxy catalog that contains all the potential hosts of supermassive black hole binaries in the local universe, and I enhanced this map with important quantities for gravitational wave detection, like the distance of the galaxy and the mass of the central supermassive black hole. And then I populated all of these galaxies with binaries and compared the strain they could produce in the most optimistic scenario with the limits that we currently have. It turns out that there are only about 200 galaxies that if they hosted a binary, they could produce detectable gravitational waves. And these are shown here. So you can see that these galaxies are relatively nearby. Most of them are within 300 megaparsec. And also the size of the dot here in this map shows the mass of the central supermassive black hole in that galaxy. So you can see that these are, they have very massive supermassive black holes. So they're very massive galaxies, the most massive galaxies in the universe. And since we haven't detected anything, we can place limits for each one of them, for the binaries, the hypothetical binaries that are in each one of them. So we can start from the strain limit as a function of frequency. So we get that information from analyzing the gravitational wave data. We know then that the strain depends on the frequency, which here we vary, the distance of the binary, which we have from the catalog, and also the chirp mass of the binary. So we can convert the strain upper limit to a chirp mass upper limit, which is the middle panel here. And then the chirp mass depends on the total mass of the binary, which I can assume, since I know the mass of the central supermassive black hole, that I know this quantity, and then on the mass ratio. So I can convert these limits to mass ratio limits for these binaries, again, as a function of frequency. And you can see that for some of the best galaxies that we can probe, the limits we can place for the mass ratio are very informative. So if there is a binary in these galaxies, the secondary black hole has to be significantly less massive than the primary. And these limits are at the level where we can exclude a binary companion for Sagittarius A star with completely independent methods. So already pulsar timing arrays provide very informative limits. Another important thing is that we can exclude major mergers in these galaxies. Major mergers are important for galaxy formation and evolution, and they're mergers between galaxies of similar mass. That means that their supermassive binary in the end should have similar mass. So we can exclude the existence of major mergers or binary produced by major mergers in these galaxies. Now, of course, as the sensitivity of pulsar timing arrays increases, our limits will become better and better. And of course, the goal is not just to improve the upper limits, but get to the detection, which, as I said, will open up the amazing possibilities for multi-messenger observations. Now, in 2019, we wrote a white paper with Luke Kelly for the Decadal Survey in the US, where we summarized all the potential observables in electromagnetic and gravitational waves of these supermassive binaries, and all the important questions that we hope to address in the next 10 years by combining the two messengers. Here I will just focus on the quasars with periodic variability that I described at the first part of the talk, and the individually resolved binaries that I was just telling you about on the limits. Now, these two methods can probe the same population of binaries. So binaries with the same mass and the same frequency or period. So we wrote a paper where we looked at what is the overlap in the parameter space of binaries where we can observe with both methods. And here I'm showing this parameter space in terms of total mass and period. The blue shaded region shows binaries we can detect with electromagnetic observations, and the purple shows binaries we can detect with gravitational wave observations, starting from the NANOGrav 11-year sensitivity and going to projected sensitivities with the International Pulsar Timing Array in just a few years, and when we will have the square kilometer array in 10 years. So you can see that now we are limited. We can do multi-messenger science, but only for the most massive binaries that are relatively nearby. But as we go, as the sensitivity of pulsar timing arrays increases, the common parameter space also increases. So we are now building a pipeline to combine the two data streams in one and do multi-messenger observations. And we are testing it with simulations. So this is still under development. But just for the final few minutes, I will just describe where I see this field going. So multi-messenger astrophysics is very exciting, and we hope that we will have a lot of excitement in the next few years. Starting from the detection of the gravitational wave background, going to robust electromagnetic detections with LSST, then finding the first individually resolved binary, finding its host galaxy and combining with electromagnetic data to do multi-messenger detections, then finding a population of binaries, both in LSST and constraining the gravitational wave spectrum. And eventually, in like 10 or 12 years, we will have LISA flying and open up yet a new window into the gravitational wave spectrum. All this will, of course, allow us to address the important questions that I mentioned in the beginning, ranging from the formation and evolution of binaries, their interaction with the gas and how that shapes the electromagnetic signatures. And of course, the goal is to better understand how galaxies form and evolve, and how their black holes form and evolve, and how they co-evolve with the host galaxy. And of course, use them as tests for general relativity and as cosmological probes. So very quickly, I will just summarize what I told you today. Pulsar timing arrays are expected to open a new window into the gravitational wave universe very soon. They probe supermassive black hole binaries, which are formed in galaxy mergers. And the first signal we expect to detect is the gravitational wave background, which will allow us to constrain how often galaxies merge, how often binaries form, and how they evolve. And of course, a few years later, we expect to find individually resolved binaries on top of that background, and combine them with the bright electromagnetic emission that we expect for these binaries, and do multi-messenger science. These binaries, we already identify a lot of candidate systems in time domain surveys as quasars with periodic variability. But overall, it's very hard to confirm their binary nature relying on electromagnetic data alone. Of course, we will have LSST that will begin operations next year, and that is very exciting, and it can give us a lot of very reliable candidates. And of course, pulsar timing arrays, especially combined with electromagnetic data, can already provide very significant constraints. And I think that the future, of course, in this field is multi-messenger. And with that, I'll thank you for your attention, and I'll take any questions.
Thank you very much, Maria, for this very clear and very interesting talk. And I think there will be questions, and there is also some clapping, which way. Okay, so let's see. If there are questions, please raise your hands or unmute yourselves. Okay, I see one hand by Apostolos Mastichiadis. Please go ahead.
Yeah, hi, Maria. Thank you very much for your talk. Very enlightening. And congratulations for your new position. Probably it's very beautiful up there, but it will be cold, much colder than in Tennessee, where you are now. I have a question about your periodicity in quasars. Are there any models? I mean, what are the physical processes that you expect that you will see? I mean, okay, you have two binary black holes. Why this will produce periodic variations? What are the physical processes? Are there any specific models, or it is some hand-waving arguments only?
So there are two main models. One has to do with these streams that come inwards periodically. So we see that the accretion rate onto the black holes is periodically modulated. So even though these simulations don't quite model, they don't have radiative transfer in the models, or at least most of them, We expect that these periodic changes in the accretion rate will be translated into periodic flux variations. The other model has to do with this gas that is bound to the individual black holes. Again, from the simulations, we see that some of the gas gets trapped around the black hole and moves with the binary. Now, if we have a relatively unequal mass binary that is not too far from a John, we expect effects from special relativity. So we expect relativistic Doppler boosts to be dominant. In that case, the smaller black hole is the one that has typically the brighter mini disk, because it's the one that it moves closer to the edge of the disk and pulls the streams inward, and it's the one that is moving faster. So when the secondary is moving towards the observer, it will appear brighter. When it's moving away, it will appear dimmer. For a circular orbit, that means a very smooth sinusoidal periodicity. So this is the easy. The Doppler boost is very easy to understand. How these periodic streams are translated into periodic variability, it's still unclear, and the models are still young.
Okay, thank you.
Any other questions for Maria? Let me ask you one more question, Maria, about this point. So besides the periodicity that you're searching, what other electromagnetic signatures are you expecting to find?
Yeah, so I went over this very quickly.
Yes.
So one of the signatures is related to the relativistic Doppler boost that I was describing. So the amplitude of the periodic variability in the relativistic Doppler boost depends on the spectral slope. So if you have a spectrum of a quasar and you measure the slope to be different in optical, let's say, and UV, you expect that you will have different amplitude periodicity in different bands. So if you have optical and UV light curves, you can search for that. Another signature has to do with this cavity in the disk. So we expect to have a deficit in UV just because we have a part of the disk that we are missing. Other models predict that you should have an X-ray excess because you have these streams that come inwards and heat, so you have shock heating. So you may have a bump in the X-ray spectrum. There are radio signatures that have to do with the jets and the base of the jet moving. So there is the spectrum. So if these black holes can carry their broad emission lines, the spectrum, the broad emission lines will shift back and forth. So taking spectra over time and seeing the shift of the lines. So these are some of the main signatures that people are looking at.
Okay, yes, sounds like too many options out there.
Right.
One more question about the gravitational background that you mentioned. As a non-expert, I'm a little bit skeptical about how one could actually constrain all of these three quantities, like the galaxy merger rate, the black hole mass function, or at least these two, based on a simple power spectrum that you detect, or the characteristic strain as a function of frequency. So is it possible to disentangle these effects, the galaxy merger rate and the black hole mass function, or not? Or what are the degeneracies?
You're absolutely right. There's a lot of degeneracy here, and people, so there is a 25-year history of people changing the models, predicting the background with different assumptions. I think there is a lot of uncertainty between how often galaxies merge and what is the mass function. Now, if one of the two evolves over redshift in a different way, there is hope that with maybe not just detecting the background initially, but detecting the entire spectrum, you can start disentangling these processes. But I think because these quantities are very uncertain or potentially biased because we have this M sigma relationship or the MM bulge, the gravitational wave background could be our best hope to make some progress on that field.
Okay. Yes, I will be looking forward to it. Thank you very much. Any other questions? I don't see any other hands raised, Maria. So thank you very much for joining today and for accepting the invitation. And hopefully you're going to visit us in Athens soon.
Thank you so much for the invitation. And yes, I look forward to seeing you in person.
Bye. Thank you very much. Thank you all for joining.